So good afternoon, everybody. So in today's tutorial session, we continue to talk about the single-phase AC circuit. As I mentioned in the lectures that in a single-phase AC circuit, each parts of the circuit, each load, can be represented with impedance. So in the AC circuit, right? Impedance, we say Z. The Z can be written into complex number forms with a resistance in series with a reactance. Or you can write it into a polar form that has the values with angle. Here we using the A to represent the angle with angle. This is a polar form. So here A is the impedance, angle and the cosine A is called the load power factor. Okay, so each load in an AC circuit can be represented with an impedance Z. It can be written into either complex number forms or polar forms. So when in polar forms, there is an impedance angle. Here, A, the cosine A is then called the load power factors. In short, PF. Of course, any combinations of the system can have their equivalent impedance and their equivalent power factors. So any parts of the network can got a total effective impedance with a total power factor. So now, in practice, in your homes or everywhere inside the buildings, we may use different types of the machines, different type of loadings, different type of usings. A typical one that, for example, the lighting systems. For the lighting systems, we may use different types of lamps. For example, incandescent lamps. Incandescent lamps, which using some of special resistance inside. Due to the heatings of the resistance, we have the light. Or we using the a fluorescent lamp, fluorescent lamps, or sometimes we use an electric radiator heater. We have the heater, or air conditioner systems, or washing machines. So each of them can be represented, with the equivalent impedance, with power factors. So largely speaking, so each of the users may be, we say, an inductive impedance or inductive load, which actually with the resistance and inductance with a power factor lagging, or a capacitive one. Capacitive one means that it has resistance plus capacitance. Its power factor usually is a leading. That means the current in a capacitive load leading the voltage across the capacitive load, while that the current in an inductive load leading lacks the voltage cross inductor load. Or the load may be a pure resistance. Now, for the 5 machines listed here, in practice, we may represent them as, here, for the first one, A, in Cadson Labs, it is can be seen as a pure resistance. Pure resistor. Power factor is almost 1. And for the fluorescent lamps, it usually has the impedance that right, resistance plus J reactance with a positive impedance angle. Power factor, usually is around, right, 0.95. Okay, so nowadays the fluorescent lamps used in our homes in the campus, so usually has a very high power factors, although it is inductive load. Its power factor is around 0.95. Okay, that means the angle is very close to 0, right? Very small. For the heaters, so most of the heaters can be seen as a pure resistor. Okay. Air conditioner systems. So air conditioner systems involves the rotary machines. Okay, rotary machines. For most it can be represented with with Langen power factor of about 0.8, right? So for most of the rotary machines, it can be represented with impedance with a Langen power factor of about 0.8. Of course, right? The rotary machine has a small power factor at the starting moment. Okay, so for most rotary machines, it can be represented with impedance with a Langen power factor of about 0.8. So maybe 0.7, 0.85, 0.9, something like that. Depends on the ratings, depends on the machine's types, depending on the machine's size, and so on. Of course, also, the rotary machines may have a small power factors, PT power factors, at the starting moment, generally. This is the case. Okay, when you study about the power the machine, so you will see that the rotary machines at the moment starting, its equivalent resistance is smaller, but it is equivalent, right? Reactance is bigger. So result in that power factors at the starting moment be smaller. Okay, so anyway, now you know that in practice, okay, so each right types of users can be represented with suitable right impedance. Okay, here just give you some examples. Okay, so this telling you how to represent a given machines or given users in a single phase AC circuit. So now before we talk about tutorial examples 1, 2, and let's looking at the data tables to try to understanding in the AC circuit, what does it mean by the right current carrying capacity? What does it mean by the cable size? What does it mean by the voltage drops across the impedance on the single phase AC circuit? So now, okay, so can you see my screens here? Okay, I think you can, As you know that we have a different types of tables, a different type of cables used, in the power distributions. Here, so this table is on the single core PVC insulated non-armored, with or without the sheath. This is the cable types descriptions. The cable has core materials, that's the conductors. The conductors material is copper. So this tables has been developed based on British standards. So here, for the British standards, for some of the single core PVC standard cables with different cross-sectional area, as listed here in the first column, when it is used in different ways, for example, in different ways in the reference method 1, which means that if the cable enclosed in a conduit in the thermally insulating wall, so if the cable is installed in such a way, then so the maximum long time continuous current allowed to carry is listed in the tables, listed in tables. So the current carrying capacity given here is the non-time maximum current allowed to current carrying capacity is maximum allowed so that its working temperature (70°) when the temperatures be when the ambient that's the beginning of it. So what does it mean by the current carrying capacity? So the current carrying capacity, okay, is the maximum non-time current allowed to carry so that its working temperature be 70 degrees when the ambient temperature is 30 degrees. Okay, that's the meaning of it. That's the definitions of current carrying capacities. Okay, so that we just consider about the thermal effects. Yeah, thermal effects. So that's why for the same cables as you see here, for the same cables, for example, 120 square millimeter, these cables, when it is used for the AC, for the single phase AC, for the DC, for the three-phase AC, and installed in different way, their current carrying capacity is different. Because that, we are concerned about the thermal effects. The cables installed in different way has different, right, characteristics in terms of the thermal dissipations. Okay, if it is enclosed in a conduit, if it is placed in an open area, okay, or it is enclosed in an insulation materials, then their heating dissipation rate will be different. As a result, with the same current, their working temperature will be different. Now, we should guarantee their working temperatures not larger than 70 degrees when the environment temperature is 30 degrees. So we should have different current carrying capacity allowed, under different installation method. Okay, so we should choose a cables whose we should choose a cable whose current carrying capacity larger than the current to be carried by the cable. Okay, so in practice, if someone asks you to choose suitable cables, you have to choose the cables so that its current carrying capacity larger than the current to be carried by the cables. For example, if we have a cable like to carry a current 200 volt, 200 amperes, then you should choose in the cables which has a cross-section area 120 square millimeter, whose current carrying capacity is 210 amperes. If the current to be carried is 200, or if the current to be carried is 190, for the single phase AC, so you should also choose in that the cable has a size 120 square millimeters. That's one principle to size the cables, choosing the size of the cables. This is the current carrying capacity. And when the cables carrying currents, because the impedance of the cables, there is voltage drops on the cables. Similar to the DC cases, in the DC circuit, we have the resistance. Therefore, we have the resistive voltage drops. In AC case, we have the impedance. Therefore, we have the impedance voltage drops. As you know that, the impedance, as we can see in next tables for the same cables above, we still with this as examples. Suppose for the cable, its cross-sectional area 120 square millimeter. When we using two single core cables, okay, for the DC circuit, its voltage drops per ampere, per meter for two conductors together be 0.36 millivolts per ampere per meter. Okay, millivolts per ampere per meter for two conductors together. This is the resistive voltage drops. However, when we use it for the single phase AC for 50 Hertz and 70 degrees Celsius, okay, you know that, okay, so the impedance, okay, the resistance of a cable changing with temperatures, and the reactance of the cable changing with the frequency. Resistance, okay, R changes with temperature, and okay, reactance X changes with frequency. You know the reactance, for example, for the inductance, which is omega L. Okay. Inductive one, okay, which is omega L, right? Okay. So the L inductance. Okay. For a capacitor, right? For a inductance, okay. And the inductance due to capacitors, okay, which is 1 over bracket omega C, right? Okay. For example, when you have an inductance L, the reactance of this inductance will be the omega here. Okay, W, we use the W represented omega here. So the omega here, angular frequency L. And the capacitor's reactance, which is 1 over omega C, right? So the reactance X changes with the frequency. So that's why we say reactance X change with frequency, resistance change, okay, with the temperatures. Then the tables listed here for the Hong Kong, it is for 50 Hertz for 70 degrees Celsius. Okay. This is the conditions. Okay. This is conditions. Remember of it. Okay. So when someone asks you to explain the values given here, you should say that this is the voltage drops per ampere per meter for two conductors together. Suppose the frequency is 50 Hertz and the working temperature is 70 degrees. And that's the meaning of it. Now, we, okay, looking at this one to see the difference. Looking at here, so for the DC case, we just has the resistive voltage drops 0.36, right? But when we applied for the, we using two single core cables applied for the single phase AC, then the voltage drops, okay, has two components. One is R, which represents the resistive voltage drop, 0.39. The other one is the reactive voltage drops, that is 0.27 millivolts per ampere per meter for two conductors together. Last one is the Z, okay, impedance 0.47, okay, voltage drop per ampere per meter. So this is the, okay, R component, X component, Z component. The R component, X component perpendicular to each other, so the Z component. Okay. So the relationship, the Z component is the R component square plus the X component square root. Okay. You know that? And you may mention, right? You may noted that for the single phase case, 0.36 resistive voltage drops. For the single phase AC, the resistive voltage drops 0.39, which a little bit larger than the DC case, 0.36. The difference here comes from the skin effect. Okay. 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 As I just said, right? So due to the skin effect, the resistance in an AC circuit is a little bit larger than in the DC case. And you can see from here. Okay, you see from here. That's the difference. For the reactance, look at here. So it is inductive one. Generally, is an inductive one. Positive values means the inductive one. Negative values means the capacitive one. Okay. And so generally, so the frequency, the larger of the frequency, the larger of the reactive voltage drops. Okay, this reactance, larger of the frequency, larger of the reactance. Okay, if the frequency double, so reactance doubled. For the resistance, okay, for resistance, so depends on the temperatures. This is for 70 degrees. When the temperature changed, this will change. So very similar to that for the DC. Okay. And you also noted that, okay, for the two single core cables installed in method 3 and 4, and for that installed in method 1 and 11, their voltage drops slightly different. That's because their temperature, their voltage drop, so impedance will be slightly different. Okay, impedance will be slightly different. Okay. And for the three-phase case, much more different. So we will explain the three-phase case, because in the three-phase case, right? So the current on the two conductors, has a big phase difference. One that I remember that in the DC case and in the single-phase AC case, the current in and the current out in the two conductors opposite to each other. But in a single phase, in the three-phase case, the current on one conductors, in comparison with the current on the other conductors, their phase angle difference is 120 degrees rather than 180 degrees. So which we explain it. You will see this in the single three-phase systems. Here we do not talk so much. So this is the voltage drops. They have three different values here, and you should know the meanings. The first value, resistive voltage drops. The second value, reactive voltage drops. The third value is the total values. In a drawing, their relationships. Okay, so Okay, so the R, X, and Z, their relationship showing in these drawings. So the R, okay, resistive voltage drops, X, reactive voltage drops, and Z is the total voltage drops. And you have, okay, this is the impedance angles. Sorry. So there is angles between Z and R. That is the impedance angles. That's the impedance angles. Okay. Similarly, for different cables, we have the so-called multi-core PVC insulated cables. Okay, and their current carrying capacity and their voltage drops will be different. Okay. Also, we may have the single core cables, armored PVC insulated cables, or non-armored one, and so on. Okay. Please, when you ask to choose the cables, use the correct type of the cables. So we have many types of cables. For example, multi-core armored cables, insulated cables with the copper materials based on the British standards 63 and 46. And so on. So the data tables shown here is just limited, okay? But there are many kinds of the cables. For each of the cables, they may have different current carrying capacity and a different voltage drops data. Okay, it depends on the cable types, including the two-core cable, single-core cable, three-core cable, or copper materials, aluminum materials, or steel materials. Armored or non-armored, PVC insulated or non-PVC insulated, with a sheath or with non-sheath, right? So many types of cables. Okay, so this is about the current carrying capacity and voltage drops. Okay, voltage drops. Now we back to the tutorials. Okay, so now we're talking about in practice how to distribute powers with cables. Okay, tutorial example 1 is a very simple, straightforward one. Okay, so the question here says that we have a single phase 9.6 kilowatt heater is supplying at 200 volts AC via 25 meter of two-core cable to British standard 630 46 table E46. What will be the supply voltage? Draw the phasor diagram for the system. State clearly any assumptions made. First, we should understanding what does it mean by this one? Okay, so the rating powers P and the rating voltage we equal to 200 volts. Okay, that's the real powers over here. Heater is a resistor R, right? That's the meaning of it. So this gives the full informations. Okay, full informations. Okay, we have a load. This load has a rating power and rating voltage 200 volts with the rating power 9.6 kilowatt, single phase one, and a heater. So heater actually is a resistor R. Okay, the power factor almost be 1. Now we're using a 25-meter long twin core cable, so multiple core cable. Okay, so 25 meters long to supply to this load. Now, estimate the source voltage required, okay, to supply to this load. Remember, in general case, the voltage source equal to the voltage load plus the voltage cable drop. Cable drop. Okay, generally speaking, in a single-phase AC circuit, distribution powers we get in the buildings, we from a source, given source, using the cables to supply powers to different load. For a given load, suppose the voltage to the load is V load. The voltage drops on the cables is V cable drop. Then the source voltage V source is the sum of these two. Okay, so based on this voltage equation, one can estimate the source voltage required when the load voltage is given and cable voltage drops can be estimated. Or if you given the source voltage, fix the source voltage, and you know the cable voltage drops, you can estimate the actual voltage to the load. Pay attention to that. In the DC circuit, it's just a simple, right? A scalar calculations. But in the AC circuit, pay attention to that's the V source, V load, and V cable drop are all constant number form. Okay, that means they are not with the same phase angles. They have angle difference in them. Okay. This is the explanations of the question itself. Now we go ahead and see in practice how to estimate the supply voltage required for a heater like this. Since it is a heater, so it is a pure resistor. That means there is no inductance here. So the voltage, the current, the resistance are all in phase, making the questions just similar to that in the DC case. Okay, now, as you know that, okay, so now the voltage to the load is 200 volts. Remember, okay, 50 hertz. Okay, not mention that, but now it is a DC, right? It is a AC 50 hertz. It is 50 hertz. Because in Hong Kong, in this local area, we are using 50 hertz AC. Okay. If you're America, they will be different. So each readings has their own standard. So now the 200 volts is the voltage to the heater terminals. And the heater has rating powers 9.6 kilowatt. Okay. So the equivalent resistance of the heater can be estimated, that is the V squared over the real power P. Here it is estimated 4.17 ohms. And also the current flow in the heaters can be estimated, which is the voltage across the heater over the resistance of the heater, which be estimated 48 amperes. Now, this means that we have 48 amperes flow on the cables. Then, which cables should be used? According to the cable table, we should choose in the cables that has a current carrying capacity be larger than 48 amperes. Suppose that the environment temperatures is 30 degrees. In most of the case, it's around 30 degrees or lower than that. That's no problems. Okay. Suppose that the ambient temperature is 30 degrees and the cables being installed in method 1, we say clip direct. Then we can refer to the table A64. We found that the single core cable, the two core cable, which has a cross-section area of conductor 6 square millimeter, its rating current will be larger than 48 amperes. Okay, so if we choose in the 6 square millimeter two core cables, in tables A64, then we found that its voltage drops per ampere per meter for the two conductors, live conductor, neutral conductor. The L here is live conductor, N here neutral conductor together. So it has voltage drops 7.3 millivolts per ampere per meter. And full load 49 amperes, 70 degrees. That's the conditions. So now the voltage drop on the cables can be estimated, which using the voltage drop per ampere per meter for two conductors together times the amperes on the cable, which is 48 amperes, times the length of the cable, which is 25 meters long given. So we can estimate the voltage drop cable be 8.8 volts. Because this is a resistive load, and the cable also is a resistive one. Note, for cables, for cross-sectional area, less than 16 millimeter square, the cable Okay, so for cables, whose cross-section area smaller than 16 square millimeter, it's right. What it drops, just has resistive values, no reactive values actually. For larger cables, it's not the case. The reactance should be for cables that the cross-section area larger than 16 square millimeter, the reactance should be considered. So you can check into the cables, right? Tables that will found that for small cables that the voltage drop just has the resistive components. So for this example 1, question 1, it is a resistive one. So the voltage drops of the cable, the voltage cross the load, and the source voltage are all in phase. Are all in phase. are all in phase. Okay, that's why we directly, right, okay, sum them together to get the source voltage. Okay, this is example 1. Now, we're looking at example 2. In that case, okay, the cables we use is lighter. That means the cable has impedance, has the reactance, and the load is not the pure resistor. That means the load has a power factor less than 1 with reactance. Okay, and the voltage drops on the cable, and the voltage drop across the load will be not in phase. In that case, we have taken account the complex number form calculations. Okay, so the question 2, very similar to question 1, but the load here is non-resistive one, inductive one load. Okay, now looking at the questions. A single phase 95 kilowatt machine, this is a machine having an efficiency of 91%, runs at 0.75 power factor lagging. This means inductive one. Okay, inductive one. Lagging, power factor lagging. Okay, the terminal voltage is 195 volts. Now, the supply voltage, the supply cable is 50 meter long single core cable to the table A61 enclosed. Now, what is the supply voltage? So the question 2 look, right, the form very similar to the question 1. The only difference is that here, okay, the machine is a inductive one, and the powers is bigger. Therefore, the current is bigger. The cable size will be bigger. The cable size will be bigger. The cable voltage drop will be with reactive voltage drops. So, what is the supply voltage? And also, it asks you that how what is the capacitor rating required to improve the power factor, and what will be the current for a short circuit at the machine terminals, assuming the source impedance will be 0.1 ohms with impedance angle 60 degrees. Okay. State clearly any assumptions made, draw the circuit and a phasor diagram for each case. So today we just looking at the first one. Okay, what is the supply voltage required? Okay. Now, with this in mind, so we can first to drawing a equivalent circuit. This is a typical equivalent circuit for power distributions. Remember this one. Okay, for any questions that that there is a source, we supply a single phase voltage. We use the cables. The cable has equivalent cable reactance, equivalent cable resistance, and the cable has a voltage drop here. We're using the VZ represented cable voltage drops, and we have the machine. The machine has equivalent resistance R and equivalent reactance X. Okay, the total voltage drops across the machine is V. Now, in phasor diagrams, the relationship between them is. So, suppose the Vs is the source voltage. The V here is the voltage across the machine, and the Vz here is the voltage on voltage drops on the cables. Then the V plus Vz equal to Vs. Okay, vector equal to Look, so the relationship source voltage is the load voltage plus the cable voltage drops. But pay attention to that, okay? That is not a simple sum up, but a vector sum up, okay? And when you're looking into the detail, right, relationship between the voltage and the current. So generally, so the V is the voltage cross the load, and the machine has a lagging power factor, which means the machine currents I, the currents in series on the cable, then go through the machines, they return to the source. So the currents which lags the voltage, machine current I lags the machine voltage V by a impedance angle theta. So the theta, comes from the power factor. Okay, the power factor is giving 0.75, right? This is the load impedance angle, which determines the power factor of the machine. Okay, so that the voltage drops, on the machine can further be divided into the VR and the VX. Now, for the cable, so the cable has voltage drops VZ. So, in comparison with the machine, the cable usually has a power factor that much lower than the load. Suppose, right, this is the voltage drop on the cables, voltage drops on the cables. So the voltage drop on cable, so the voltage drop on cable can be divided into two parts. One is the resistive voltage drops, which is in phase with the current. One is the reactive voltage drops, which is perpendicular to the currents. So the Vx perpendicular to the current. The VR, in the phase with the current. Then there is a phase angle difference between the Vz and the I, current I. So this is the impedance angle of the cable. Cable impedance angle, that is the determine the cable current lags the cable voltage drop. Machine's impedance angle determine the angle difference between the machine's voltage and the machine's currents. Okay. There is phi. Sorry. Okay, now, so we're looking at, based on the equivalent circuit showing above and the phasor diagrams drawing here, we can have a quick estimation about the voltage required. So now the input powers, the power of the machine given is 95 kilowatt. Because of the efficiency issues, that the machine required powers is the rating powers 95 over the efficiency, which is 104 kilowatt. This is the real powers required by the machine. So you know that the real powers is the currents, voltage, power factors of the machine. So now we can estimate the current go through the machine using the machine's real powers over the voltage and the power factors. Okay, the real powers is the voltage currents by cosine theta between them for the machine. So you can estimate that for this machine, that the current required is 714 amperes. Now, checking into the tables we just talked, you can find that usually choosing a cable, its current capacity larger than 714 amperes. But closer to it, but larger than. So from the table, one can find out that the cable with a cross-section area 630 square meter, whose current capacity 720 amperes and 30 degrees environment, which is larger than 714 amperes. Okay, so for these cables, you can check into the cable voltage drops per ampere per meter, which has the R parts. Resistive voltage drops 0.094 millivolts per ampere per meter. Reactive voltage drops 0.25 millivolts per ampere per meter. The Z values, 0.27 millivolts per ampere per meter. Millivolts per ampere per meter. Millivolts per ampere per meter, you can say milliohms per meter for two conductors together. Now, the total voltage drops on the cable is the total current, 740 amperes, times the per meter's voltage drops times the 50 meters long, which has a value 9.6 volts. This is just the voltage drop values. The cable has impedance angles, as we show here. The cable has impedance angle. The impedance angle can be estimated with the resistance, and reactance. So this is X over the R. X over R is the tangential, phase angles. So the impedance angles can be arctangential estimated, which is almost about 70 degrees. Similarly, the machine's impedance angles can be retrieved from its power factor, which is given 0.75. So the machine's machine's impedance angle 41.4 degrees. So the theta is estimated 41, and the phi here is estimated 96.4. Therefore, the supply voltage, source voltage, is the sum of the load voltage V plus the Vz, which is a vector assumptions. Because with the impedance angle and the voltage drop, impedance angle, voltage drop, one can change the values into the complex number forms, or just using the pointer forms. Here, using the triangle right theories, that the source voltage, square equal to the load voltage square plus the voltage drop square of the cable minus 2 times the voltage load and cable voltage drop, the cosine angles between the V and the Vz. The cosine angles between the V and the Va. This angle. This angles is 180 minus 67.4 minus 41.4. So the angles between the V and the Vz, which you can prove that. So the 180 degrees minus the phi minus theta, because the Vz here in parallel with the Vz here. So the phi here, is the same of this angle, right? Of this angle, same of this angle. So the external angle here is the internal angle, right? So because this angle equal internal angle, right, minus this one. So 180 minus the external angle. This external angle is this angle, minus this angle. You can calculate the source voltage required under 3.6 volts, while the voltage to the load is 195, and voltage drop across the cable is 9.6. 195 is the V, and 9.6 is the VZ, and the VS, which is not the direct sum, right? But get the triangle relationship between them. You can use a different approach to the calculations. Okay, some students may familiar with the polar forms. Some students are familiar with the triangle theories. Some students can to get so because you know the voltage drop here. Okay, so you can write. Okay, you can write. Okay, the V equal to the 195 with angle 61 degree. The VZ is 9.6 for examples. So what does this mean? This means that for the load, it has a voltage 195 volts with a voltage phase angle 41 degrees, which is the theta. For the cable voltage drops, it has a voltage drop 9.6 volts with a phase angle 96 degrees, and the source voltage and VS which 0 degrees. That's the meaning of it. Okay. In polar form, the source voltage values 203.6 volts, but the impedance angle we suppose is 0 degree. Okay, that's the drawings here. Then, in comparison with the source voltage, the voltage cross the load, the voltage cross the cables, their values, and phase angles. So with these three in mind, you can write the V into a polar forms or into a complex number forms with R and X parts. You can write the VZ with R and X parts. Then R together, X together, you got the complex number form of VS. Then you can got the total values of VS. Okay, so you can use these three to do the calculation. Okay, with this. Okay, so here just to perform the one method to get the right source voltage. You can use the polar forms given here and change into the complex number forms to estimate the source voltage. Okay, depends on So today this is the end of today's tutorial session. So you take times to review the tutorial example 1 and 2. Try to make you familiar with the complex number or polar form calculations in terms of the voltage. Okay, that's the end of today's tutorial. See you next. See you the next lecture.